Hello everyone, this video is on cyclic groups. A cyclic group, the name is derived from cycle, means loop, repetition. A loop has something to do with repetition. A cyclic group is a beautiful notion of finite groups. And in the study of groups, we'll see that finite groups are more interesting than the infinite groups. Now let us take a close look at finite groups. Let G equals to E a dot dot be a finite group of order n. Next, let us consider these elements a square dot up to a to the power n. Then because G is a group and by closure axiom of group, these elements must also belong in G. Not only these elements, but e to the power n plus 1 must also belong in G by closure axiom. There are n elements in G and there are n elements in these collections, and all of these n elements belongs in G. Therefore, e to the power n plus 1 must take one of these values. Therefore, e to the power n plus 1 is equals to e to the power I for I lesser equals to n. Now because G is finite, the number of elements in G are limited, and that led to this repetition. E to the power n plus 1 is again repeated from one of these n elements, and this repetition led to the cyclic groups. Next there are n elements in G, n elements in this collection, and all of the elements in this collection belongs in G. Therefore, we have either an equals to e, or for some I less than n, we have ai is equals to e. If ai equals to e, then a to the power I plus 1 equals to ai times a, and we have ai equals to e. Therefore, a to the power I plus 1 reduces to a, and likewise a to the power I plus 2 reduces to a square. And next, let us consider the case a to the power I equals to e for I less than n. Let us present this in the diagram. A to the power square dot dot, we have a to the power I equals to e. Therefore, a to the power I plus 1 is again a, and it forms a cycle. Therefore, this group a up to a to the power I is a cyclic group, and there are I number of elements. Next, let us consider the case a to the power n equals to e. Again, we present this situation in diagram, and we have a square a to the power I dot 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 e to the power n equals to e. Therefore, e to the power n plus 1 is again a, and it forms a cycle, and this group is also a cyclic group. There are n elements in this cycle, and we have n elements in G, and because these n elements are distinct, this collection is equals to G. So in this case, the entire group G is cyclic group. Let me clarify this situation with an example. Let G equals to 1 minus 1 I minus I be a group, a finite group. Take the element I and consider these elements. I square is minus 1, I cube is minus I to the power 4 is 1, and therefore I to the power 5 is again I. Let us present this situation in diagram, and we have I square, I cube, I to the power 4, and I to the power 5 is again I. So this gives a cycle, and therefore this group I square, I cube, I4 is a cyclic group, and therefore G is a cyclic group. And we have seen that the entire group G is generated by a element of G, that is I. I generates the entire group G. Such a group which has a generator, and whose elements are related in a cycle are called cyclic groups. Next, we take the notion of cyclic groups to the infinite groups. The infinite groups have infinite number of elements, so there is no possibility of repetition of the elements of the group. But nonetheless, the infinite groups can have a generator. The entire group can be generated by some elements of the group. In that case, we call the infinite groups a cyclic group. For instance, take a group Z plus. This entire group Z plus is generated by 1 of Z. 1 plus 1 is 2, 1 plus 1 plus 1 is 3, and so on. And the entire group can be generated by 1. So this group is cyclic group.